We're going to discuss a topic that you'll be using a lot throughout the rest of algebra and algebra 2, and that topic is functions. And more importantly, today we're going to talk about how you can recognize a function. You've been dealing with functions already, but you just haven't recognized it. We're going to put the word function to define something that you've already been using. So let's first look at the definition of a function. A function, in order to understand a function, you have to understand a relation. We've talked about relations already as being a set of ordered pairs. We'll look at the first part of the definition of a function. A function is a set of ordered pairs. But there's something even more specific to it. It's a set of ordered pairs such that each element of the domain is paired with exactly one element of the range. So look down here below at these three different sets of ordered pairs. All three of them are relations, but one of them is not a function. Can you tell which one? In analyzing the first one, notice that all of the elements of the domain, -3, 0, 2, and 5, are paired with only one element of the range. -3 is paired with 5, 0 is paired with 7, 2 is paired with 12, and 5 with 19. However, over here in the second one, you'll notice that 2, an element from the domain, is paired with 3, and 2 is also paired with 12, meaning that this set of ordered pairs is not a function. The last set of ordered pairs over here, you can see that each element of the domain is paired with only one element of the range. 4 only has the element 16 paired with it, while 2 is only paired with 8, 0 and 0, and -2 and -8. Let's look at functions in a different way. You know that functions are a set of ordered pairs. Well, haven't we also learned that equations can be used to represent a set of ordered pairs? When you look at y equals 3x minus 4, the first thing that usually comes to your head is this is an equation. But you should begin to think of it as a function now. Okay. We know that the table here suggests that we would want to manipulate x to be -2 and then solve for y. So when I replace x with -2, I'm left with y equals -6 minus 4 and y equals -10, suggesting that when I input the value -2 for x, my output is -10. And I can do the same thing for 0, and you would notice that my output would be a -4. And if I did the same thing for 2, you would notice that your output would be a +2. And now let's see what happens as well when you plug in 4. When I plug in 4 for x, when I make my input for x to be 4, as the table suggests here, I'm left with y equals 12 minus 4. So y is equal to 8. So this set of ordered pairs is a relation, rather it is a function, because every value in the domain is paired with exactly one value in the range. And don't forget that this equation is representing this entire set of ordered pairs. So we begin to think of y equals 3x minus 4 as the function that represents this set of ordered pairs. We'll look at some more functions here in a little bit, but we're going to introduce a new type of notation. Rather than using y equals 3x minus 4, we're going to change the notation to say f of x equals 3x minus 4. That's how that's read. Now don't think of this as multiplication. It's not. It is its own variable. Instead of using y, we're going to now start using the variable f of x. f of x is what's called Euler's notation, or sometimes referred to as function notation. And f of x is just a new variable to represent our dependent variable. So not much has changed here, other than the fact that we have a new notation. Let's take a look at what f of x looks like. When we're talking about the function f of x equals 3x minus 4, rather than looking at the equation that we looked at earlier and having a set of x and y values, and plugging in x values and receiving outputs for y values, we're now going to use this notation to place the value that we want x to be in the dependent variable. So previously, where I would say, what does y equal when x is equal to negative 2? And I would plug a negative 2 in for x and solve for y. All of that can be said by simply asking, what is the value of f of negative 2? Which just simply means replace x with negative 2 and evaluate. F of negative 2 is equal to negative 10. Again, just a fancy way, a new notation to say when x is equal to negative 2, y is equal to negative 10. So what is f of 0? Well, f of 0 means plug in 0 for x and evaluate. F of 0 is equal to negative 4. Let's try some more. What is f of 3? That's one that we didn't do up here. When I replace the independent variable with 3 and evaluate, f of 3 is equal to 5. Let's try some more challenging functions. Up to now, you've only looked at linear functions. Well, actually, let's hold off on that for a second. Let's look at a different function. F of x is equal to 2x plus 5. Go ahead and find the value of f of 1, f of 2, and f of 3. And as you can see here, I've evaluated this linear function for 3 different values. I've evaluated the linear function for when x is equal to 1, replaced x with 1, and solved. I've evaluated it for when x is 2, replaced x with 2, and solved to get 9. And I've evaluated it down here for when x is equal to 3. I replaced x with 3 and solved to find that the value of f of 3 is 11. Let's take a look at one that's a little bit more challenging here. Let's peek at f of x is equal to x squared minus 4x plus 5, which adds a little bit more interesting challenge. If I wanted to evaluate f of 3, I'm going to replace all of the x's in this nonlinear function with the value 3, leaving me with 3 squared minus 4 times 3 plus 5. Let's not forget our order of operations, which asks us to evaluate exponents first. So 3 squared is 9. I can then evaluate multiplication. And now I'll do subtraction and addition from left to right. 9 minus 12 is negative 3. And negative 3 plus 5 is 2. So f of 3, for my new nonlinear function here, f of 3 is 2. Again, this is just another way of saying if I'm not looking at this as function notation, if I think of this as an equation, this is just a fancy way of saying when x is 3, y is 2. But here we've now eliminated this equation notation, and we're coming over to this new idea of function notation, which will be a common theme in all of algebra. The last thing we'll talk about today is how to determine whether the graph of a relation is a function. And we use a special test here that's called the vertical line test. The vertical line test will tell us if the graph of a relation is a function. So if you plot the ordered pairs on the coordinate plane, will that graph can you determine whether or not that relation is a function? And it's done by simply doing the vertical line test, which means if you cannot draw a vertical line so that it intersects the graph in more than one place, then the graph is a function. Let's take a look at an example of some that are functions first. So here are a few graphs of functions. Notice these are all functions because the vertical line test, when I do the vertical line test, I'm drawing a vertical line on the graph. And this vertical line is only touching the function in one place. And same thing over here, as you see this nice curve function, no longer looking at a linear function, but this vertical line can only touch it in one place. And same thing over here with this function. Anywhere I draw a vertical line will only touch the graph in one place. And you'll see the same thing over here. So what does a relation look like that's not a function when you graph its set of ordered pairs? Here are a few examples. Notice here in this relation, when I draw a vertical line, it touches the relation in two places. Again, recall that 5 has an output of 2 and 5 has an output of -2. The value in the domain 5 is paired with two different values in the range of 2 and -2. And you can see the same thing over here. When I draw the vertical line, two different ordered pairs on the relation touch that vertical line, proving that this relation is not a function. This one over here touches in three different places. Again, it fails the vertical line test because the vertical line touches the relation in more than one place. And finally, this fourth one, you can see vertical line again touches this relation in two different locations, showing that it is not a function. For homework tonight, please complete from page 229, numbers 6 through 11, and 29 through 37.